So let's start with those guys. I think you all know IPCC. IPCC is the International Panel on Climate Change. It's a group of scientists which is tasked to collect bibliography, papers, documents, and reports, and produce the state of the climate to United Nations and to the Conference of the Parties. So what they do is they collect thousands. I personally know one of the lead authors, and I know how they work. So they work based on science. But in the end, out of those thousands of papers, they had to make summaries, because we know that politicians, they don't want, let's not say they don't have time. They just don't want, they're too lazy to read in-depth documentation. So they had to make summaries, short summaries that someone in the bottom room can get at a glance. So what they did, they just said, I have to, okay, that's a little better. In their semi-last summary, they said that the global warming is likely to reach 1.5 degrees Celsius by 2052 if it goes on like it's going now. And that climate-related risks for natural and human systems are higher for a global warming of 1.5 than at present, but lower than at 2 degrees Celsius. So they are saying something which we know very well, that some people still, well, there's still someone not trusting in this, but that's not our problem, not at least of this course. And they say this risk depends on the magnitude and rate of warming. So let's see what they say. They talk about increase at a given rate, the rate we measure, we witness now. And they talk about magnitudes and rates. So they're talking about trends. If we translate this in what we talked about those days, it means that we need accuracy to correctly get a trend. Of course, we need relative measurements, because most of climatology is based on relative values. We can have a full morning about the difference between absolute and relative measurement. With a relative measurement, you can get rid of many uncertainties. Who is interested, please, let's have a few words about it. And then they have to be, there's need of comparability. So if they need to be close to real values, and we need to get the rate, then we need to somewhere evaluate uncertainties. If they need to be comparable, then we need to make them traceable. Not only, but they put numbers there. And those numbers are about temperature. So let me say that the interaction between the climate and metrology community started about 10, 12 years ago in two fields of research, environmental research. One is chemistry. There was a huge demand from the Global Atmospheric Watch program to have traceable measurements in order that the stations around the world, I think we also have one in the Zeppelin in Neolison. It's a GOES station. There is another one near the Everest base camp, and many around the world. They need to be comparable. So they approached the BIPM. They went to, maybe you remember, BIPM is divided into committees. They went to the Committee of Mass, which deals with chemistry, and they asked, we need traceability. But immediately after, Since the key quantity to describe climate change is temperature, it was then, maybe you recall a picture I put in the opening, it was the committee on temperature, on thermometry. So temperature metrologists like me, I was involved in the determination of the Boltzmann constant before doing this different activity. So we started to say, those guys are talking about temperature. So are they pointing at us? Is there something we can do? We know how to measure temperature at the microkelvin level. Well, they don't need the microkelvin, but they need something in support to their studies and their way to alert the world, because everywhere you see 1.5, 2, and these are degrees Celsius. So we need to measure air temperature. Air temperature has been measured for years, centuries, decades, and unfortunately this is what we well know, and it's based on anomalies. I don't go into the climatology of this, the principle how we obtain such graphs, and even with poor measurement, because for sure in the past measurements that were made only for meteorology, there is a large difference in between meteorology and climatology. So, but nevertheless, there is so much data that tells the same story, that those measurements are reliable, those trends are reliable. But now we need to make better measurements, much better than in the past. But we said we need to measure air temperature. There is not a definition of air temperature. Maybe this may surprise you, but there is not an international, I don't even mean a standard, but there is not a definition of the measurand air temperature. There is not a way, an agreed way, to evaluate the uncertainty budget for air temperature measurements. And there is even not best practice or guidelines, international guidelines, how to calibrate the thermometers in air. We know well how to calibrate thermometers in liquid, or as we heard yesterday, everything is clarified. We have procedure, we have uncertainty budget, we have standards, we have devices, but there is nothing similar for the thermometers in air. So can we evaluate the uncertainty budget, which is required to get the trend, hopefully to get the trend in a shorter time? So unfortunately, we're not in person, but normally when I put this point, I would like to see the reaction of people. And I don't know if this is possible. I don't think so, but do you agree that a thermometer measures the temperature of the air? Is there someone against this sentence? So let's go on and see what happens. So are we sure the temperature measures, the thermometer measures the temperature? Are we sure it is the temperature what we're measuring? And are we sure it is the temperature of the air what we are measuring when we just put a meteorological thermometer in the air? So I immediately jumped to the solution, but then you will see that there is lots behind that. I prefer to say that a contact thermometer gives an indication, even not, I don't even say it's a measurement. It gives an indication of its heat equilibrium at that time, in that place, under those conditions. This is the only thing I am okay to say, nothing more. I don't pretend to say I am measuring temperature, but we record temperature, we publish temperature, we think in temperature, and so on. By the way, speaking about temperature, of the 7 base units, the more I can say I'm a little bit expert in temperature. We went down to really in deep, but that's my personal opinion. Temperature is the quantity that was introduced by humans because we cannot explain something in a different way. Just to explain, length is a portion of the space. Mass is an amount of substance. It's a number of atoms. It's something that exists in nature. But temperature, as well as current, is a number of particles of charges going on in a conductor or among two. So temperature is something that humans needed to explain other 2 complicated phenomena, and they just call it temperature. And by the way, it comes from the Latin tempera, that it was the right time to beat the iron, when it was proper for making any kind of tool, from swords to everything they needed. That was tempera. So let's go on with this, because this equilibrium, well, by the way, what I write here is in bracket contact thermometer. You will see a little bit later that this matters. But unfortunately, technology we use is based now on contact thermometers. Very few are non-contact system, LiDARs are. So the equilibrium has, well, there is no time for one morning of thermodynamics and physics of thermodynamics, but the equilibrium is influenced by convection. So it's the heat exchange, which is due to the wind speed, the heat transfer coefficient, the surface, even the surface area, which is touched by the wind blowing, and temperature gradients. If the wind is colder or warmer than the thermometer, then the step is such that we introduce further errors, uncertainties. But then you have the conduction. The conduction, because the thermometer is a physical object. It conducts. It conducts also through its shelter, its screen, and the solar shield that it has around. If it is warmer, somewhere there is a conduction point. Again, gradients. Radiation. So these are the three main ways energy is transferred, because unfortunately, again, temperature is energy. Not by chance we use the Boltzmann constant now for defining. So radiation is the nightmare. Radiation is what manufacturers, they try to get rid of in the best way they can for air temperature measurement, because radiation can introduce really a number of errors, most of which are, well, all of them are asymmetric. So they are only on, the distribution is only on one side. So it's not a symmetric correction, because it adds heat with respect to, bear in mind, our measurement is the air temperature, not linked to the radiation of that day. This is why we also don't have the definition. But there is also phase change, phase transition, condensation, evaporation. Let's not talk about the Arctic, but in a normal European station where you have the natural grass, in the morning you have some humidity and moist, and then it evaporates. And when it evaporates, when the sun comes, it evaporates, it removes heat, and the temperature goes down. But it's an error. Then you have transit heat transfer, heat capacity of the thermometer, the mass. You also have self-heating. There is a current going in the thermometer. But also, well, I don't go into all the details, but please consider, the probe is not adiabatic. It has imperfect geometry, stagnation, laminar, turbulent, mass, heat capacity, Well, I don't go into all of them, but self-heating. Just to give you an idea that all of them, they introduce issues in the definition of what I measure, and all of them, in principle, are components of uncertainty and should all be studied or minimized, or they are just negligible. Some of them they can be negligible, but they exist. Consider the similar problem to any measurement you do. There is something likely less dramatic also for pressure, for example, not to mention wind speed and not to mention precipitation. Now, I don't go into, again, the physics, but if the ideal thermometer in ideal gas, it's quite complicated in terms of modeling the physics, the real gas and real thermometer is a full nightmare. Forget it. We will never be able to make the complete understanding and model of each thermometer in every condition. We do this for very specific case when you go to definition of temperature, and then you have to model the very millikelvin level, sub-millikelvin level. But normally for air temperature, it's just impossible. Forget it. And there are dynamic correction function and so on. Moreover, the contact thermometer is calibrated, as we have heard yesterday, in adiabatic conditions as well as we can. Why we need adiabatic conditions? Because when you need to measure your temperature, your mother tells you, keep the thermometer for some minutes. Why do you have to keep the thermometer for some minutes? Because it needs to be in adiabatic condition with your body. Because in the end, as we said, the thermometer measures its own temperature. So until its own temperature, it is not the same as your temperature, you're not making a correct measure. What does it mean it's the same? It means there is no heat exchange between you, your body, and the thermometer. So they are in adiabatic condition, no heat exchange. This is what we do in calibration. We wait, we realize, as we heard yesterday, we realize and check that the conditions are stable and uniform in order to avoid time changes of temperature or even gradients and convections. And then we start the calibration because we are sure within some uncertainties that the reference and the device and the calibration, they are at the same. Again, this is the same for pressure and for many other quantities. But then you take your thermometer, you put it in the field, and the field is everything but not adiabatic. The world is not adiabatic, unfortunately, or luckily. So are we sure we can keep the traceability? Because it was calibrated in a way which is not the way you're going to use it. And that was a scheme of the traceability chain, fixed point, we seen yesterday. But at some point, we move from liquid to air with the magic, according to the procedure of the lab. In order to try to address all of those problems, well, I don't want to spoil you the end of the story, but I'm not going to give an answer to those problems today, because there is a huge effort internationally, which I will mention later on, in order to try to address these issues. So the part of the uncertainty is due to this non-perfect definition of the measurements. We have other problems with the definitions of measurements. For example, who is into permafrost will know that the GCOS talks about thermostat of permafrost, while the Global Cryosphere Watch now is talking about permafrost temperature. We don't know, well, I am into the permafrost best practice group. I co-chair it, and we have not got exactly why they were talking about thermal state. Probably they wanted to say something bigger, which is not only temperature, but we cannot measure a thermal state, which is better. Since this is an ECV, I think you all know what ECV, essential climate variable. It should be something that we can measure, not just, or that we can observe against some sort of agreed standards. I don't mean every standard needs to be a SI, but thermal state is not only, but if you give a look at the Global Cryosphere Watch glossary, then you see that every time they talk about the permafrost is the ground that remains below or at 0. Maybe now you're getting from our lessons. This is, if you go to the web page of the WMO Global Cryosphere Watch, please give a look at this. There is not 1 degree Celsius written in the correct way. Not one. You read 0C, below 0 watts, degrees. Okay, that's for sure an error, and so on. But then, one of the definition of the active layer talks about thawing and freezing. So you say, yes, of course. The active layer is that portion of the permafrost that seasonally thaws and freezes. So it becomes water, and then in the winter it's ice again. It's solid again. But don't you think there is something not aligned between the definition of permafrost and the definition of the active layer? Can you guess where is the problem? The problem is that freezing and thawing are not at 0 degrees C. Because we are not talking about pure water. We are talking about salty water. If you are in marine permafrost, we are talking about debris. We are talking about water that melts and freezes within a number of particles and components and rocks, particle, whatever it is, but it's way never at 0. So this is another point where we are really discussing, and we had more than 1 year of discussion without great results, in order to convince the community that they should talk about that they should change actually the definition of permafrost, not that of the active layer. The permafrost is that soil that remains, that thaws and freezes, or whatever it is, it's solid, it contains water, ice, but you cannot talk about the 0 degrees C, or you completely change the definition of the active layer. But this goes into the measurement, because thermometers, they measure the 0 degrees C. And you will see that the thawing plateau in temperature is not at 0. So are you sure that there is not an error in your system, or it's actually the permafrost which is not thawing, is not making the phase transition at 0 degrees C? So that's an issue which should be defined in a better way, in order that when we go to calibrate the permafrost thermometer, and we really need 0.0 something for the permafrost to well detect year by year if we have a problem, if the permafrost active layer is going down, because in the end, when we have to move a house because the permafrost is disappearing, or there are infrastructure problems, it is not due to the 0. They are not due to the 0. They are due to the fact that they are thawing, that is melting. So we need to face a different definition in order that we correctly measure that. And this is why there is an interesting activity within the global climate observing system, which is the definition of climate reference data. Because we're talking about references now, not only ECV. We're talking about such data which comes from a reference station, for example, what we would like to think, if it is possible, also to have in the Arctic. Reference station is something that correctly measures, that really goes into the heart of the measurement and the value of the quantity with full uncertainty. It is traceable, it is able to quantify the variability and change over time. It means measurement system must be stable, maintained, recalibrated, no issues in the aging or the drift of the thermometer, of the electronics. You have to recalibrate, you have to go and check it. So only in this way. We don't mean every station has to be like this, but at least please go and try to solve your problems. This is what GICOS tell us. And that was the signature where everything started of 2010. This is a picture that was actually the WMO, Michel Jarreau, Secretary General, and that was, let me say, our boss. It was the director of BIPM at that time. It was when the WMO said, we need traceable measurement, we need this. And this is why in the roadmap of our Committee for Temperature, we decided to talk about air temperature. So it means that the world level committees, they say we need to solve this problem. It is not a problem we technically have in the weather station of Advent Island, for example. It is not just a problem of a couple of sensors which they're not working. No, it's an international problem. I just quickly go on this, but maybe in the second part of the day, we will see it a little bit later. Everything I said now, it's about contact system. Non-contact systems, they are really promising. And there are non-contact systems for precipitation. By the way, the GICOS says that for climate, we need two key quantities to measure. One is temperature, one is precipitation, to make climate serious. Both of them now, they have promising new systems which allow to make non-contact measurement. With a non-contact measurement, for example, you get rid of radiation. You get rid of many, many other effects based on the fact you're doing a good measurement. But unfortunately, the system are still not able to reach accurate values, saying uncertainties of 0.1 degrees are really, really challenging. But this is promising. Keep your ears open. Instead, what we have done, we provided a sort of uncertainty budget. That this is if some of you knows, this is the Copernicus program of the ACNWF, which is the European Center for Medium Weather Forecasts. The Copernicus is the climate component. C3S means Climate Change Services. And this is the European network of weather and climate. And we provided with an overall Excel sheets for completing the uncertainty budget. And you can see here data logger, uncertainty drift, solar shields, precipitation, quantities of influence, data, metadata, okay, what is the status around, the calibration sensitivity, the self-heating, the resolution, and so on, all the components. In the end, we know it is impossible to put all of them. So this is why we also added a sort of level of completeness that tells the reader, well, we have been able to detect uncertainties within 50% of what we should have done. But there is an interesting action by the European Institutes of Metrology which is this project, which is running now. It's called ATM, Air Temperature Metrology. And we started with the pilot study. We still don't know, we never had a discussion on how every laboratory tries to calibrate the thermometers in air. And then we will go to proposed definition, practical of air temperature, uncertainty budget, and so on. This is an attempt to solve. And this is Europe, but also the BIPM started to think. And in 8 November 21, so only recently, it may surprise you, but only recently, the world started to think about, we need to understand what is air temperature. And okay, don't go into this. So that was the first part of my talk. I will make it quite quick. In this last part of the training, I want to show you how actually, practically, we work as metrologists in support to environmental science, with some application and projects which are running on. I will be quite quick. Please get it as a movie. If there is something that you're interested, we can talk later on. So let's talk about metrology and meteorology. There are two similar words, and in people's view, metrology has to guarantee I'm buying the correct amount of salad, and meteorology is just whether to take umbrella or not. This is in people's view, but actually it is not like that. There are world institutions that now you know, and there are scales, levels of interest in both the two areas of science. Now you know a lot about metrology. We spoke a little bit less about meteorology, but it is based on really a number of measurements from different platforms and instrumentation. It's huge. We have 54 ECV to try to detect our climate. It's not only meteorology then. You see biosphere, cryosphere, it doesn't deal with meteorology. They have some properties. They must also be feasible. We don't want to measure something impossible. The WMO has this very nice building in Geneva. It hosts the Global Climate Observing System, the Global Cryosphere Watch program, and other programs like the GOES, the GO, and so on. We see that we met, we cooperate together, and this is, for example, the list of metrologists now, each of them from a National Metrology Institute, which are working in the WMO. So I'm also happy to be chair of one of the expert team. But other colleagues, now they are involved to provide support for guidelines, measurements, training, comparison, and so on. You see that we also develop and prescribe and recommend activities, for example, the air temperature. Now let's go to the actions. This is where we try to support environmental science. New instruments, for example, the step from Stevenson to compact thermometers, intercomparison, metrology for high mountains or polar environments, validation of extremes, influence quantities for field measurement, calibration, references, and so on. All of them, they've been addressed by a large European project, which is called Meteomet, Metrology for Meteorology, which I was happy to, and which is still running. It is a 10-year project in the amount of about 10 million euros, where we try to group all the European Institute of Metrology and start to do something. What we're going to do in Niolison next week is linked to this project as well. There are parent projects, including the air temperature projects. The COAT project is the one we are going to do in Niolison for intercomparison, air and climate reference station, precipitation, and so on. I don't go into numbers, but it's really, really a huge project with manufacturers, university, research centers, and all the European Metrology Institute. Recently, Meteomet also extended to other areas in the world, and you can see that we also point Svalbard, because here we have this calibration laboratory in Ny-Ålesund, which is working. But we also have an intercomparison in South America, another one is starting in Africa. So we are really supporting comparison of instrumentation and laboratories all around the world and projects. That was our work recently, with the protocol, etc. Now I really go very quick to a number of activities that they are going on. For example, this is an interesting project on non-contact precipitation gauge, which we think are promising, but still now there is no way to make a calibration. We're working to provide guidelines how to calibrate this acoustic, optical laser, this durometer. They're called non-catching, so they don't collect the precipitation. And we have to make a number of really measurements and analysis, even to detect what the drop is. What is the shape of the drop? Metrologically, we also made experiments in the field and tried to set up a calibration system for that. Another project is the climate reference station. It's a new project that started in 2020, actually in 2021, where we will provide guidelines for the global climate observing system, how to set up a reference station instead of just buying instruments and deploy them in the field. This is based on comparing instruments, making calibration of sensor, including shield effects, finding a suitable solution with 100 meters of radius in order to avoid disturb from surrounding obstacles like houses, building, and so on. We work for the radius zones. We started our polar actions in 2014 with the GRUAN, the GCOS reference upper air network. We went in Ny-Ålesund to calibrate the system to check the radius zones before they start the flight, the ascent in the air. And this is done in a very challenging humidity and temperature range. Under the Horizon 2020, we work for understanding the clouds. The clouds are really the next most important scientific understanding for our climate. Clouds really set the climate, and we still know very few about clouds. So we started to work with the Polytechnic in Torino, and they are providing small, very small radius zones, which they can float in the air. They will reach the clouds, and they will be trapped into the clouds, measuring thermodynamic properties, temperature, pressure, humidity, wind speed, but also they know the overall fluid dynamics of the clouds. That's quite an interesting, again, project. Something of direct interest was a conclusion of this project on the albedo, the reflected radiation on the thermometers. I think, Sebastian, this is also of your interest, because we talk about protecting the thermometer from the direct solar radiation, but very rarely we consider the backwards radiation from the sun. They are not manufacturers, they don't make the same effort to protect the thermometers from the below radiation. And we measure something. We really measured this by comparing two identical groups of different thermometers and shields in the same meteorological conditions, so close, but by removing the snow from one area and leaving the snow in the other area. So these are a couple of identical instruments in the same weather conditions, meteorological condition. We also had an intermediate point to measure in between, but here we left the natural soil. What we have seen is incredible. When the sun comes, you have up to 3 degrees of difference only due to the backward radiation. And this is the difference between identical couple of sensors. So some they react more, some they react less, but all of them they react in a larger way than during the night, where you only have the, let's say, calibration uncertainty. Precipitation, I said it before, we studied the effects in terms of overcooling errors. And this is how, when it was done with artificial rain in Denmark. If you're interested in this, I can also give you information on the results of this experiment. These are a number of cooperation with manufacturers when we also developed specific instrumentation with them. We started with the WMO, the sighting. It means there is guidelines. There are guidelines about how to correctly position thermometers. For example, if you have the opportunity to set up a station in a really wide area, don't put it close to a river if you can, so that you have at least 100 meters of free area. And this is given by the WMO normatives, without trees, without water, without buildings, and without roads. And we actually measured the effect with 3 identical experiments, and you will see that we have 100 meters pointing to a road, 100 meters pointing to a building, 100 meters pointing to trees. We got all the information. We luckily understood that the normatives now they're overestimating, but there is still need to really go ahead in this direction in order that there is a way to correct for this. Of course, there are many kinds of road. We know all of this. Extreme values. We were called, personally, we have been involved into the validation of 2 temperature extremes that they were measured in 2016 and 17. One was in Kuwait and the other was in Pakistan. And by chance, they were all 54 degrees, the highest temperature ever recorded in Asia, the 3rd highest temperature recorded in Earth, and possibly the highest temperature recorded at that time with modern technology, because the first 2 higher values, they are from 1913 and 1922. That value is one of them. And so we had to, the instrument underwent a strong evaluation process with uncertainty, and we did by comparison, we did by absolute values, because we had to detect their behavior at 54 degrees. So an intensive work was done. There is a publication. I can tell you that the highest temperature was the one in Kuwait of 5378. I don't remember. That was the temperature that we recorded. And the same it will be done, unfortunately, in August 21. We have an alert from a station in Sicily, and we scored, unfortunately, 48.8. Now, I don't know, but it seems that the thermometers are arriving. They are arrived at INRIM. INRIM, my institute, is the institute that WMO identified to perform such kind of investigation. There are not so many institutes in the world which are collaborating directly with the WMO. You have seen in the previous slide, there is NPL, UK, SAM in Spain. We have Korea, INRIM, France for what is about marine application, and few other, PTB, of course, for radiation. Now, let's go a little bit on something of interest for this community. Permafrost. This is permafrost in high mountains. And what they see is the active layer, it's deeper thermometers. They are all of them, they're showing trends. All of them. But the point is that this trend is of the same order of what is acceptable for the drift of thermometers. If you recalibrate thermometers after years, you can get a similar trend. So is this observed warming or is due to instrumental drift? So again, they are stable. This is why, nevertheless, we are working with in climatology with these mathematical tools, but nevertheless we have to calibrate the instruments, especially when we need to detect small trends. And by the way, to go back to the question of Francesca, there is another aspect. If we calibrate instrumentation, if they are traceable, if they are comparable, we are able to detect the trends really in a quicker way than waiting for decades for the signal. So what we have done, we went to for example, they give us graph like this and they say how it comes. Is this change possible, or something happened to the thermometers at 70 meters? Is it permafrost disappearing from in this case it's called the permafrost table. So what we have done, and I think we repeated this for other years, we went to 3,000 meters. We brought a metrology lab there with all the traveling standards. Now you understand well what we mean. So there were traveling reference standards, working standards that we used to bring up there. They should have been a little bit robust. And we brought their liquid bath, readout system at the millikelvin level, and so on. Sorry, this is a repetition. And we were able to calibrate on site without removing the data logger. So in the same condition, with the same wires, 100 meters of cables, 50, 12, according to the depth of each sensor. And you can see here, maybe you recognize Chiara is taking part in this training. She was in charge to make the calibration of this system. We were, let's say, happy, and now we are improving the instrumentation in a way that it can perform a calibration in 1 day only, because at the beginning we needed to stay 3 days, but now we are reducing time and we did it. And maybe you can see here, okay, this is the readouts. Permafrost, we calibrate the sensor between -7 to +10, something like this. This is the point at nominal 3 degrees Celsius, 2.8594. So let's take the 9 millikelvin as our sensitivity, but actually the 3 thermometers, the reference standards, they were, you see, this is 10 millikelvin. We were in between 3-4 millikelvin. For the overall uncertainty, you get this 5 minutes of stability and you get the data from the other thermometers. So you are happy you're doing a calibration within 3 millikelvin for all the 36 thermometers. And what we have done, we really reconstructed the shape, which before it was like this, and then we were able to correct it in a most coherent way. We gave support to the Global Cluster Watch. Something similar was done with a transportable chamber that was made in Torino. It was shipped to Kathmandu. Then from Kathmandu, it went to Lukla, and then to Lukla with porters. This is the climatic chamber with the porter, whom unfortunately also added other weight because they were paid for the weight they were bringing up there. And then we reached the 5,000 meter pyramid where we installed the instrumentation. Now they are able to make calibration of thermometers all around the Everest area. The Khumbu Valley is called. So that was our other mission. There is still a lab there. So they are now able to check the number of weather stations here and there in the valley. When they need, they have a procedure to make the calibration. Now let's go to the final part, which now is really directly of your interest. And this is unfortunately what we see in the planet. This is not time series, this is actually measurement. This is again a reason why we need to calibrate the thermometers, because we need to compare not only the trend in a place, because the time series are separate trends in separate places, but now we want to have a picture of our planet at a single day, for example. But again, you see, we are talking about anomaly. Now, there is a problem in the Arctic. This graph is from Marion Maturilli. It's a time series in the Svalbard. You see, just from 1994, modern instrumentation, everything well kept, science. But as a famous man here around says, climate change comes first and faster in the Arctic. This is terrible. And we had to talk about this at the Arctic Circle. It was a halfway diplomatic and scientific event, but we brought metrology there. Those guys, they all come, I think you recognize Carmen, me, Chiara, and other people from Metrology Institute. This is Volker from PTB. That was the vice president of Euromet. We went to the Arctic Circle to talk about what metrology can do actually. And immediately after, we started cooperation with our Polar Science Institute, Istituto di Scienze Polari, and Mauro, this picture of you. And we opened the first laboratory ever for metrology in the Arctic. This is for science and research. We have to consider the opportunity also to extend elsewhere, not only for science. The first result, this is the climate change tower in Ålesund, 30 meters, 4 measuring points to detect boundary layer and atmospheric physics. The first real results, you can find it in these two graphs. We adjusted, we corrected the gradients and the differences among the 4 thermometers. Vaisala only provides a 1-point calibration at 20 degrees. We went with this installation, we put the thermometers, and now we are really improving time by time. This is all experimental, there are not prescribed guidelines. So time by time, we are also improving, we are understanding some factors to make a better measurement. But the real result is that now you have a coherent gradient, which before was awkward, was unusual, was not correct. They were not aligned. Now we have really calibrated using the calibration course. There was an error there. The calibration corrected for the error. Next week, we will be again in Ålesund. This is the field that was prepared for hosting international comparison of thermometers and the solar screen there. And we discussed all of them during the Arctic meteorology workshops, which again, I invite you to attend on 8 and 9 June, in a couple of weeks now. So, just to summarize what metrology does for climate and environment. There is a growing involvement of national metrology institutes. That's really the story, step change from 2010. We are extending the areas of interest according to the need coming from, let me say, your community. This is why workshops are important, conference, speaking each other, visiting installation is important. We need to speak, we need to understand where problems are, and maybe metrology cannot help, but maybe we can start to propose projects and even get funds, why not? There is a new and strong cooperation with WMO. We also have members of WMO now in the IPM expert team. We are making new laboratories, new equipment, field sites, research installation. There are really new activities, not just deploying a number of weather stations around and leaving them to their, and abandoning them just taking some numbers. No, we're doing something strong, robust, and reliable for the coming years. We work for best practice from really official regulatory material, as you see, what we will do for air temperature, but also by just improving how we calibrate the thermometers at the Vascari lab year by year, by mistakes, no problem. But then we have done the same with permafrost. The first year it was a total nightmare. We made a lot of mistakes, but after that, for example, we didn't took enough into account the self-heating of the 36 thermometers. Then we did. More training, like we're doing now. More scientific production. Let's have publications together. National and international projects. There is money floating around. Let's try to interact and stop this money and have projects together. So I just conclude with a couple of pictures. The global warming is a reality. Measurements have proven it. Accurate measurements are really necessary to evaluate trends and rates in a quick way, and traceable measurements are required to establish comparability among all the number of different systems. There is really a new philosophy in the WMO, which is called the Earth System approach. We are just facing the fact that we have a single Earth. It's a unique object, it's a unique measurand. So let's try to understand this measurement for different points of view, but let's compare all of them. And I just want to show you the different points of view we were starting. The meteorologists, when they approach a weather station, they used to say, well, what's that? I'm used to the millikelvin. So this is what normally we are thinking about, this very poor level of resolution, which is not actually. But on the other side, the meteorologists said, yes, you can talk about resolution sensitivity, but if I don't put the hands on those instruments, nothing works here. So the message is to remove this difference. I want to show you this picture that we took in, I think, 2014 now. This is the AWI Gruen installation in Jolesund. It's the station where the radiosondes are filled and they fly. I think you can recognize some people here. But what is nice of this picture is that we had the banner of our MeteoMet project. I don't know why. Meteorologists, they were all on one side of the picture, and meteorologists, let's say climate and researchers, they were all on the other side. That's really crazy, but it's how this picture came. So my message is that we have to remove and keep on working together. So that's my overall message also to this audience.